Hello, and welcome to AMAT362 at UAlbany. This class is going to occur online, and for these purposes, I'm recording these lectures so that you can refer to them later. I'm going to try to update and post videos on this website, which is amat362.github.io. You'll see here a source for our syllabus for this semester, again indicating how this is online. If you want to schedule office hours, please email me or Brendan Mallory, who will be our TA. There are no required texts for this course, but I highly recommend considering purchasing the Anderson Ceppolino Valco. That's this first one here. But you'll get by just fine using the lecture notes I provide you, and then occasionally referring to maybe Grinstead and Snell, which is available freely online as a PDF. Further details are going to be there. Part of the purpose of me pre-recording these lectures is so that we can spend most of our lecture time going through the worksheet. Every lecture is going to have a worksheet, and then problems we don't get to are going to be left as homework. Today, we're going to have 8 questions, and I hope to be able to get through at least most of the first 5. All right, so we're going to take a quick journey over to my notepad. Traditionally, I'll be writing out these lecture notes for you in the videos so that you can sort of practice following along and taking notes with me. Since I already recorded some of this and I noticed some problems with the video, I'm just going to run through lecture notes, which I've already written out for you. So I always like to begin my classes with a sort of bird's eye view of the course. And this is with the intention that hopefully it entices you to want to actually study the material involved and not just view it as a requirement. But I do want to start off by sort of defining some of the terms in our course title. So you'll notice this is AMAT362, which is probability for statistics. Which by its very name means that there's probably a difference between probability and statistics. So let's go ahead and try to highlight those. I think of probability as the mathematical study of models for uncertainty, meaning you have total control over what the model is. You need to specify it, you can define it, and you can define what its properties are. On the flip side of it, we have statistics. And statistics means that we sort of study data out in the real world. And then we try to reverse engineer what was the underlying probabilistic model that generated that data. Now, you might ask yourself, why do we even have anything that's uncertain? Often, if we pay attention to Newton's laws, everything is governed via some deterministic equation where you just calculate all the forces involved and then a determined output as a consequence. But we know that that isn't always the case. And moreover, we have situations where it's just impossible to know what's going to happen. Suppose I go out to a restaurant and I want to know what's the probability that I get COVID. Who knows? It depends on if there's somebody actually in the room and whether or not they're sort of breathing or sneezing or what have you. So uncertainty exists, and then we try to come up with ways of modeling it. But all of this sort of fits into the broader perspective that there is some interesting interaction between math and reality. So namely, probability sort of resides almost exclusively in the realm of mathematics. It's ideal. It's sort of well-formed using an explicit set of equations or what have you. And so with these equations and sort of idealized assumptions, this gives us ways of thinking about reality. And, this wouldn't be any good if somehow reality didn't actually display to us that she is under the hood sort of modeled or behaves according to mathematical principles. So in that sense, I think of reality as being also the source of evidence of our mathematics, that somehow, even though math is generated by humans, flawed humans who need to make assumptions and then use their own particular notation or ways of thinking. Nevertheless, we see this surprising fact that people who are separated by cultures and time and who speak even different languages end up coming up with the same models for reality because they study reality and they see ways of modeling it. And then this process just continues again and again. As we know more, we can come up with more models and so on and so forth. But broadly, statistics sort of assumes that data is given to us, so it's coming from reality. But before we can get to that, we need to first understand probability. So before our first breakout session, I want us to consider the following 4 questions with the idea that each of them are going to illustrate some aspect of probability that we're going to study in this course. And so the first question is, what's the probability of a 4 of a kind? So this means I'm got a well-shuffled standard 52 card deck, and I am dealing you 5 cards. That is some sort of experiment which results in the outcome of you having 5 cards, and you're asking, well, what's the probability that those 5 cards contain 4 cards which all have the same sort of face value? So 4 2s, or 4 kings, or 4 jacks, or 4 queens. So we'll spend some time trying to figure out what that is. The second question, which is, how much money do you need to make to be in the top 1%? And then let's just start here with the assumption that you're looking at the USA. So you basically query a random person in the United States, and you want to know, how much money they make. Obviously, if we look at all income earners, by its very number, we know that there's only a 1% chance that they're in the top 1%. But what is that amount of money? And how do we sort of summarize the sort of distribution of incomes that are above 1%? And then moreover, what happens when we condition on those income earners that live in New York? We obviously have New York City with Wall Street, one of the sort of hubs of worldwide capitalism. What does it mean to be in the top 1% when you condition on the assumption that you're only talking to New Yorkers, or maybe you're only talking to people in New York City? The third question that I want you all to consider is, what's the probability of life on Mars? And in particular, what does it mean when we use the term probability in this question? And so just what's your own personal assessment of what the probability of life on Mars is? And then finally, the question is, how many people should you date before settling on the one? Again, assuming this is something you want to do. And this is, of course, a deeply personal question, but it's sometimes fun to think about this from a strategic or mathematical point of view. And somehow this idea being that the one is the best one for you. All right, so, we're going to take about 15, 20 minutes and breakout sessions to think about that. All right, so pretending that already occurred, so let's move on to the solutions of each of these. So the 4 of a kind question can be a very tricky one, and maybe some of you have already done it in another class, but let's go ahead and revisit a strategy for solving this problem. So let me call this is a strategy. That strategy is that you should be more concrete. So imagine I refine the question and I say, I've got a shuffled deck. Imagine I hand you, 5 cards. What's the probability that the first 4 cards are kings, and then the last card is a non-king? I mean, by necessity, it has to be a non-king because there are only 4 kings in a deck of 52 cards. Well, you know, here we have the usual thing. So I ask, what's the probability of the first card being a king? Well, there are 4 kings out of a deck of 52. So there's a 4 out of 52 chance of that first card being a king. So now, sort of assuming that that first card was a king, what's the probability that the second card is a king? Well, there are now 3 kings remaining out of 51. So there's 3 out of 51 chance for that. Similarly, for the third king, there's going to be 2 kings remaining and 50 cards left. And then finally, we're asking for that fourth card. We've got 49 cards left because I've already given away 3. There's only 1 king left, assuming that these first 3 were all kings. So what is the probability of that fourth card being a king? Well, there's only one way in which that can happen, and that's 1 out of 49 is the probability for that. And so I write for this last one, 48 out of 48, because there are 48 cards left and any of them will do. And one nice way of writing out this fraction is to use the notion of factorial. So there's 4 factorial. Well, that's 4 times 3 times 2 times 1 equals 4 factorial. Similarly, I've got down at the bottom 52 times 51 times 50 times 49. So that doesn't go all the way down to 1, which is what you'd need for 52 factorial. But I can kind of get at that number by looking at 52 factorial. And then I realize that I need to cut off 48 and below. So I call that 48 factorial up top. And you can see that 52 factorial with 48 factorial on top, that's equivalent to writing this 3 numbers in the denominator. Now, there I was being very, very specific. I said I wanted the first 4 cards to be kings and I wanted the last one to not be a king. Of course, that's not the only way you can get a 4 of a kind. Consider this case where you get 2 kings, a non-king, and then 2 more kings. Writing out the probability for that, the first 2 numbers are the same because it's the same event. But in the second, or I should say this third number, I have 48 out of 50 cards, which are not kings. And so the probability that that third card's not a king is 48 out of 50. And then now I can continue going on. I said, okay, well, now there's 2 cards left. They're kings out of 49 remaining. So 2 out of 49. And then again, 1 out of 48. And notice that each of these, fractions, just comparing, are different. So you might think that there are different answers, but if you actually check, you can see that by reordering 4 times 3 times 2 times 1 and putting that all together, I get my 4 factorial. And my 48 out of 48 cancels, and then I'm left with the same denominator, 52 times 51 times 50 times 49, which is the same thing as 52 factorial, where I then cancel out the remaining 48 factorial by putting that up top. So in particular, these are the same. Now, how many ways are there of being dealt 4 kings where you don't necessarily care about the exact order? Because in each of these events, I did care about the exact order. Well, there are 5 possible ways, which comes from the fact that there are 5 possible positions for the question mark. It could be here, it could be here, it could also be here, here, or here, and that's 5. So then I just take 5 times this number, which was up here. And that gives me the probability of getting 4 kings. That's the probability of a king 4 of a kind. But suppose, again, I didn't care about it being a king. There are 13 possible face values. And that goes from just counting ace through king through queen and jack and all the way down to 2. So then I need to multiply this by 13 since there are 13 choices. So we'll go through more elegant ways of driving this number, but this hopefully helps jog your memory a little bit about how this all works. So for the question of top income earners, we've got this, you want to think about there being this sort of distribution of incomes. And you've got the Jeff Bezoses of the world who are out here. And then we have, a lot of like very ordinary people, like, I don't know, you or me, somewhere around here, who knows? So these are sort of your sort of quote unquote average people. And so this motivates one of the other themes of our course, which is that often probability just isn't about counting cards, but rather it's about studying the distribution of a continuously varying quantity. In this case, the quantity being income. You can see that there are all sorts of different incomes possible, but if we kind of study the distribution of possible incomes, we get this sort of curve. And this is the notion of a PDF, probability density function. Anyhow, from 2018, I think, and to be the top 1%, you need to be making over 430,000. I think maybe now it's up to 500,000. And then for New Yorkers, it's was 550, but now it's 600, even $750,000 a year. You might ask yourself, what should a fair distribution of income look like? Should it look roughly uniform? But how do you have a uniform distribution when there is no upper bound to how much money someone can make? Or maybe you want to look at something that's more shaped like this, where there are essentially the lower third and upper third of people are more tightly together, rather than here where the lower third and upper third are maybe more far apart. Either way, this is just something for you to think about. So I love this life on Mars question because it illustrates that there are sort of differing schools of thought on what probability means. So let me just add that, on what probability means. So in particular, traditionally, a lot of people think of probability as, you flip a coin a bunch of times and you count how many heads you get. So that's an example where you repeat an experiment multiple times and then you count the number of sort of successes. Maybe in this case, a success being you're getting a heads. This is what's called the frequentist school. And for the life on Mars question, it really, in some sense, challenges the frequentist perspective, because how would we determine what the probability of life on Mars is from a frequentist perspective? We would have to run a bunch of experiments. In this case, it would be the creation of the universe. Run it multiple times and then count, and how many of those universes did life arise on Mars 13 billion years after the Big Bang. Assuming that we want to sort of talk about probability of life on Mars now. There is sort of an alternative perspective on what probability means, and this sometimes goes underneath the heading of what's called Bayesian. And this is the idea that probability isn't just about repeating an experiment a bunch of times and counting the frequency. That's why the term frequency comes from. But rather it represents your degree of belief. Maybe it's not surprising that Thomas Bayes, the one who Bayesian is named after, was a preacher. So someone very firmly ingrained in the church, where he thought about belief all the time. So for example, instead of life on Mars, you can say, what's the probability that it's going to rain today? That just sort of should be calculated by your degree of belief in that statement. And however you arrive at that degree of belief is an open question. All right, so I always love, this question of how many people should you date before settling down? I heard lots of answers, 1, maybe 3, maybe 5. And I always sort of shock them when the answer is actually 12. And, again, you should take this all with a grain of salt, but the purpose of this question is to be modeled after something that was historically called the secretary problem, but to have a sort of more neutral name, I'll choose to try to use the term candidate problem. So the candidate problem is basically this. Imagine you've got a series of applicants coming in, and they sort of approach you. So here's you. In some random order. And let's assume there is some notion of like total ranking of who is the best person for you. So maybe you'll meet the third best person for you first, and then you'll meet the 77th best person, so not really a good fit at all, next, and then maybe you meet the 13th best person. And at this point, you're now thinking like, gosh, that first person was really good. But then you meet number 2, and you might say like, oh, great. Like, this is great. Number 2 is much better than 3. So let me go ahead and settle on this one being, quote unquote, the one. But again, these numbers suggest that number 1 is still out there. So how do you strategically approach the problem of being approached by people and then either accepting or rejecting them with the idea that you want to eventually land on, the person who is your absolute best, your soulmate? And it turns out, of course, it's really hard to do, and there are good strategies and bad strategies. Apparently, if you believe in this sort of solution, and what we can go over it later in the course, the idea is you should interview 12 people and reject them all, with the idea that you're kind of building up a sense of what's out there. And then the first person better than the previous 12, that sort of trial 12, you should accept. And it can be shown that this actually leads to something about a 1/4 or 25% chance of happiness. So, and that's probably actually the best you can do, but it makes a lot of assumptions, which we can talk about later. All right, so all of these examples are meant to sort of illustrate an idea, which is that the model for probability, which is this is the fundamental of probability is the notion of a random variable. And so a random variable you want to think of as, it's something where you have an experiment, flipping a coin, dating someone, etc., and the set of possibilities varies. That's why we say variable. We don't know what it is. It's variable, but it's constrained to live inside of something called a sample space. Omega. And in each of these examples, we can kind of go through, if I draw a card, just a single card from a deck, then my set of possibilities are the cards in that deck. And if I want to talk about what's the size, and that's indicated by these vertical lines of the sample space, well, it's 52, because there's obviously 52 cards. But now when you move to draw further cards, there are fewer possibilities. And notice that this was the thing which was in the fraction or denominator of those answers earlier. Suppose I ask a random person for their income. So here the sample space is, someone can make $0 or they can make, up to $1 trillion per year. And notice that this quantity is continuously varying. So some sample spaces, you can't really talk about size in the sense of counting, the number of elements, but you can talk about volume or area or something like that. Go to Mars and look for life, either yes or no. So there's sort of a binary outcome. And then you can, marry the first person you date, and then you can ask, well, what's the outcome being that this was a person in your list of ranked potential mates. And so that lands between 1 and n, where n is the number of people. So the sort of moral is that in probability, we always need to clearly identify the space of possibilities, omega. This is our sample space. And necessarily, this is going to be something that we write down using sets, and then we want to talk about subsets of these sets. And those are going to correspond to events. So let me just bullet point some set theory notation in case you haven't seen this already. So we have X, looks like kind of like a sideways, an E, a little e. That sort of looks like an epsilon. That's Xn is an element of omega, Xe omega. Then we also have a subset B, which corresponds to this subset notation. Now, in probability, we think about this. So this is sort of the probability interpretation. So we want to think a subset is corresponding to an event. And that could say, you draw a card, you want a card that's above, has face value above a 6. Maybe you're playing blackjack or something, and you want to go for sort of at least a higher card, or maybe you want a 8 or 9. So what's the probability of drawing a card whose face value is larger than 8? So that would be an event, and then you count the number of elements in that event to get the probability. Additionally, we have things like A superscript C, which in set theory, we just think of as the set of elements not in A. But in probability, we then have this interpretation of it's the event where something does not occur. So thus, we have this sort of a complement. And so, of course, we're going to get to this idea that either an event occurs or it does not occur. And so this gives you a notion of comparing complementary probabilities. All right, a couple more bits of notation. So we have A, sometimes called cup, but it's really A union B. In set theory, these are elements that are either in A or in B. And so if you look at this sort of picture here, I've got my sort of sample space of possible outcomes. I have an event A and I have an event B. And so I want to think of A or B as the union of those two events. So basically, here's an event where A occurred, but B didn't occur. Here's an event where B occurred, but A did not occur. And what happens where they both occur? Well, that's represented using what's called the intersection. So here we have A intersect B. And so these are going to be elements that are both in A and B. And so we think of this in terms of a probability as this is an or, and this is an and, or both in, so both occur. And of course, in my little picture here, I've got A, I've got B. I'm going to look at where they both occur. So that's this middle part here. It's A and B. So one of the first things that's sort of important for reasoning about unions and complements and intersections is this thing called De Morgan's law. And De Morgan's law basically says that, if I'm interested in an A complement B, the complement of this sort of intersection here. So imagine I've got my sample space here, And I want to look at, got what I use, the sort of salmon color. So this is A union B. If I want to know what's outside of that, maybe I'll use this sort of light green. You know, this is right over here. And of course, I can also express this in terms of the intersection or the overlay of two other pictures. So, you know, I've got, again, trying to keep this here. So here I've got if I've got A in red, maybe I can use this sort of light yellow. So that's going to be, let's say, complement. And then I'm going to intersect this with what's happening over here. And then I look at B, which I had in green. Here's B. And then I look at the complement of B. So let me use, I'll use maybe purple. If I sort of stack these on top and look at what's conjoined between them, so what's common between them, the intersection of the yellow region and this slightly moved over purple region. So I imagine stacking these on top, then I can see that what's left over is exactly the stuff in the green. And that's all just De Morgan's law. Now, this may feel really abstract, but there's actually a really nice situation where this occurs in a common puzzle. And this is the star battle puzzle. And so the instructions for the star battle puzzle are that you need to have a star in every row, or sorry, every column. You know, this being a column. And a star in every row. And moreover, you can't have two stars touch each other in the sense that, like, if I have a star here and a star here, that's not allowed. So this is bad. But every solid region has to have at least one star. It has to have exactly one star. So in particular, you know, if I had a star here, then this would mean that it's not a star here. And if I had a star here, then I could not have a star here, here, or here. And so if I look at the intersection of where there's not a star, then I get these two dots on either side. And so that just comes from sort of carving out the space of possibilities. So a similar story goes here with the sort of three stars. If I think about what is the intersection of the excluded neighborhoods, you can convince yourself that since there has to be a star somewhere in these three boxes here, so there has to be a star somewhere here, we don't know where, and I look at the intersection of all of their excluded neighborhoods, three right next to each other leaves only one excluded possibility right here. And of course, if this were down in the middle, there'd be one on the other side. It's always sort of symmetric, just like how this one is here. So how do you go about solving the star battle puzzle? Well, again, you need to always consider complements. Where can a star not be? Well, if there is a star here, necessarily, there has to be a star inside this little one of these spots. So either here or here, we don't know which one. And there's only one star in each column. That means there cannot be a star all the way here. And similarly, since there has to be a star somewhere here, that means there's not a star here. So in particular, that possibility is excluded. And so this means that the star that I just put down there has to be there. And so by doing this sort of thing, you can start ruling out possibilities. And again, once I've got one star there, I now know that there can't be any stars here, and so on and so forth. So this all just sort of illustrates De Morgan's laws. All right, so returning just briefly to the notes to kind of summarize this up a little bit. Here I've got places where a star could be in green. So here, imagine I have A, and that means there's not A somewhere in these eight cells here, or I have a star in B, and that means I need to not have a star in B in these here. So if I consider what is the intersection of these, I could see that it's just these that have mutual overlap. And so that means when I go through and I want to start eliminating possibilities, I say there's not a star here, not a star here. So can exclude these 4 spots. Assuming that I've got this really solid region here, and that means that there has to be, a star in one of these 2 regions. So this game, which, the 2-star version appears in the New York Times called Two Not Touch, is really just an exercise in thinking about De Morgan's laws. All right, so there's one more sort of bit of thing, a few more bits of terminology I want to go over with you, which I didn't get to in class proper. So it's this idea of, some more special cases. So I want you to consider, so when we have A intersect B equaling the empty set, this means that we sometimes say A and B are disjoint. The idea that this is the empty set. Which you want to think of as the set with no elements. This is the set with no elements. And sometimes we need to consider this in more generality. So we can consider this situation, which is, suppose we have a bunch of sets. So A1 intersect A2, intersect all the way up through AK. Let's suppose this is equal to the empty set. And what we say is that set A1 through AK are pairwise disjoint, or sometimes called mutually exclusive. All right. One more bit of terminology, because it's related to cards, is this notion of, some sense you want to think of A union B is sort of almost like an addition operation, which I guess in this case corresponds to, just to draw a little again here. So imagine I've got my A, and I've got B. So here their intersection is empty. And we've also got a situation that's pertinent to cards. So I call this sort of a study of Cartesian products. So imagine we can think of any element of the set omega. So this is useful where any element of some set omega can be specified with two let's say two features. So here's an example. So if you think of omega being a deck of cards, this is actually naturally equal to the rank of a card along with its suit, with the idea that this is sort of a king, queen, jack, 10 all the way down through, let's say, ace, with the idea that ace is 1. And then here we have our usual, hearts, diamonds, clubs, and then also spades. So there's 4 suits. So here's a situation where a deck of cards we can express as a Cartesian product of the rank and the suit. And this is useful because if we want to count the number of cards, I can just count the number of ranks as there are, and also count the number of suits and multiply this together. And so this is 13 times 4, which is 52. So there's one more bit of information, which is going to be useful when we talk about the axioms of probability, which is the notion that, so we want to think of union and intersection as operations defined using 2 sets. So the idea being that, I've got a set A and a set B, and then I can return, using the union, A union B, or intersection, I get A intersect B. It turns out these operations play well together in the sense that, they're symmetric, right? So A union B equals B union A. They're associative in the sense that A union B union C is the same thing as A union B union C. And they're sort of distributive in the sense that A intersect B union C is equal to A intersect B union A intersect C. And also I can look at A union B intersect C, and I'll get A union B intersect A union C. And I encourage you to draw pictures for these. All right, but unfortunately that's it for today, and I look forward to seeing you in class on Wednesday.